And here we go. So remember, we're doing essentially area between two functions. So the last ones we did were essentially between a function and the x-axis. So now we're going to talk about essentially two functions where one of them is not necessarily the x-axis. Can you all hear all that in the background? Should I put a mic on, or can you not hear that? Okay. If background noise gets to be too much, let me know. But anyway, so we've got these two functions, 4x minus x squared and 1/2 x to the 3/2. So no matter what two functions you're working with, the first thing we need to figure out is where they intersect. So we need to set these two functions equal to each other. Now in this specific case, whoops, that's not the function. In this specific case, we actually can't do that by hand. Like I actually don't know how to do that by hand. In terms of any questions you'll find on your exam, you'll be able to do them algebraically. But we're going to have to do this in our calculator. So I'll show you how to do that in case you don't know. So what we're going to do is I'm going to go to my little calculator doodad. And so if you want to pull out your calculator really quick, or if you just want to watch. So if we want to find where two functions intersect on a calculator, what we can do, and notice at the very bottom it shows you what buttons I press in case you missed what I said. If you hit the y equals key, and then you put the two functions in, so we're working with 4x minus x squared, and then you have to put the other one in a different line, but the other one we're working with is 1/2 x to the 3/2. Let's go ahead and put those fractions in parentheses just to make sure it reads it correctly. On a newer one, it shouldn't matter, but especially if you have an older version. Oh, it's not showing as much of the key history as I thought it would. Oh well. So you type those two functions in, and I mean, you don't have to sit there and watch it graph them, but you could just jump to the calculation. But let's go ahead and watch it graph them very slowly. There we go. So if we want to find where these two intersect, what you're going to do is you're going to press second and the trace button, which is right next to the graph button. So second trace, and then you can either scroll down to number 5 or you can just hit number 5 on the number pad. Now, if the only two functions you have in the y equals key are the two functions you need, then you can just press enter, enter. If it's not, you're going to have to scroll up and down between the functions that you have in your y equals key until you pick the ones that you want. But since we only have those two functions, I can just press enter, enter until it says guess at the bottom. Once it says that, we're going to essentially press the right or left arrow keys until that little like blinky flower dude gets to approximately where these two functions intersect. And it doesn't have to be perfect, but get as close as possible. So now that like little blinky flower dude is about at the right spot, hit enter, and it tells me where they intersect. So this tells me that these two functions intersect at x equals, let's say 3.12. So if there's ever anything that you can't solve by hand, or shall I say algebraically, you can do that in your calculator. But again, any exam question, anything like that, will be able to be solved algebraically. You don't have to use your calculator. Anyway, so jumping back to this. So we found that these two intersect at 3.12. And let me even write use calculator in case someone's looking at this later. There's no real way to do that algebraically, especially not nicely. So notice that the interval we're told is just x is greater than 0. We're not actually told where to stop. So if you're not told where to stop, and this is included in that process that we wrote down the other day, if you're not told where to stop, you're going to stop at the intersection point. So essentially the interval we're going to work over is 0 to 3.12. We're just going to stop wherever that intersection point is. Now here, we don't need to split this up at all because that's the only interval we have. So we just need to figure out which one's on top and which one's on bottom for this. Now we do have it graphed in our calculator already. Well, if you put it in. But let's do this algebraically. I'm going to keep doing it algebraically, even though it's an either or situation. But if you wanted to do this algebraically, you pick a point between 0 and 3.12. Absolutely any point you want between those two numbers. I'm going to pick 1 because I think it's nice. You're going to plug that number into both functions. So we'll have 4 times 1 minus 1 squared is 3. And then 1/2 times 1 to the 3/2 is 1/2. The reason you do that is because you want to figure out which y value is larger. 3 is larger than 1/2, so our top function for the integral that we need to calculate is going to be f of x. If you were to do this by graph, because again, we kind of already had it, we have that our graph looks something like this, and the parabola is on top of the other function. The parabola is the 4 minus x squared, which is exactly what we found to be on top. So now we're ready to actually form and calculate our integral. So remember, it's always top function minus bottom function. So the top function here is 4x minus x squared. And then we're going to subtract the bottom function. I suggest always putting the bottom function in parentheses just to be sure that things are going to be read right and negatives are going to be distributed if you need to distribute negatives, anything like that. Now, I think I said this before, but I'll reiterate it. In terms of questions like these, at this point, you can plug that into your calculator if you have a calculator that has the capacity to do so. And I don't need to see any more work in terms of the integral. So you could punch this into a calculator. You'll get the answer is 5.906. Now I'm going to write down the antiderivative because, of course, if you don't have a calculator that can do it, you'll have to do it by hand a little bit. So you'll need to find the antiderivative, plug in the top bound, subtract what you get when you plug in the bottom bound. So if you were to do that here, let me just write down the antiderivative in case anyone's curious. Our antiderivative would be 2x squared minus 1/3 x cubed, and then minus, and I know I always need to work this one out a little bit. So the 1/2 comes along, add 1, you'll get 3, you'll get 5/2. Divide by 5/2. Same as multiplying by 2/5. But the 2's cancel each other out, so this will end up as 1/5 x to the 5/2 plus c from 0 to 3.12. So if you plug in the top bound, subtract what you get when you plug in the bottom bound, you should still get 5.906. Questions, concerns about that one? Okay. So we've got one more. So I'll leave this up for like 5 more seconds. All right, so the last one we've got then is we've got find the area enclosed by x squared and the square root of x on the interval 0 to 4. So here we're given a full interval, so we're not going to need to end it ourselves or anything like that, but we might need to split it up. So we need to find where these two functions intersect. We can do this one algebraically, and this one actually has a very important thing that I want to say because a lot of people will do this actually incorrectly. So with these two, I can do this algebraically. Now, the main thing I want to get rid of is that square root because working with square roots is gross. I can kind of work with a squared, but working with square roots is not fun. So if I want to start solving this, if I want to get rid of a square root, I have to square that. But if I do something to one side, I have to do it to the other, so I have to square the other side. So we'll get x equals x to the 4th. Now this is where a lot of people will go a little bit wrong here. Some people will say, well, I want to divide by x. And while technically, if you think about it correctly, that's a logical step. But a lot of times people won't think about it correctly and they actually lose an answer. So I'm going to do this the correct way, and then I'm going to talk about why you can't do that or why you should be very careful to do that in a second. So try to avoid dividing by variables. Instead, what you should do is you should collect all of the variables on the same side. So instead of dividing by that x, let's subtract it over to the other side. And then you can pull it out because now all of those things have an x in common. And now that you have a product of things, either x is 0 or x cubed minus 1 is 0. So we get x is 0 or x is 1. Also remember, since it's a cube, when you cube root something, you don't get a plus minus. You only get a plus minus when the power was positive. So those are the two numbers we'd get from that. Now, going back to what people do wrong a lot. So let me zoom in a little bit, and I'll zoom back out in a second. But I'll run out of space if I don't zoom in a little bit to write this down, if it will let me zoom. There we go. Goodness gracious. So a lot of times what people will do when they have something like x equals x to the fourth, they'll want to divide by x. And they'll get 1 equals x cubed, and they'll get x is 1. Cool, cool. That was totally an answer. But notice that when I did this, I didn't get x equals 0 as well. And where'd it go? It's an answer that makes that true. So why did it disappear? So the thing is, when you divide by something, you can't divide by 0 because that just makes the world explode and me cry at night and you just don't want to do it. So when you divide by x, you're essentially assuming that x is not 0. So you're kind of losing that possible answer of 0. So since x equals 0 is actually a solution here, when you divide by that x, you lost it. Now, if you say, okay, well then if I divide by this, I have to assume x is not 0. So let me also then consider the case when x is 0. That's fine, but that's what a lot of people don't do, is they don't think about it correctly to then actually consider the case of when x was 0. So anyway, when doing these algebraically, if you want to divide by a variable, try not to. Do everything in your power to avoid dividing by variables, because sometimes it can lose answers. Anyway, so we found x equals 0 and x equals 1. So 0, we don't quite need to care about because it was an endpoint already. So even if you did that incorrect algebra, it kind of would have saved your butt. But anyway, but we do have to split this up in terms of 1. So we're going from 0 to 1, and then from 1 to 4. Now this is where we need to find which one's on top of the other. Again, I will do both ways, algebraically and graphically. You only need to choose one, whichever one floats your boat. But just for the sake of doing the full process in each case, I'm going to do both. So pick a number in both of your intervals, whatever number floats your boat. Plug it into your functions. So your functions are the square root of x and x squared. They're given to you in the problem. So if I take the square root of 1/2, I'm going to get 0.707. And if I take 1/2 squared, I'm going to get 0.25. Which one of those two numbers is larger? 0.707. So that means for the first, my f of x, my square root of x, is on top. And then if I do the same thing for x equals 2 for the second interval, square root of 2 is approximately 1.414. And then 2 squared, so let me write it a bit more fully on this side. And then 2 squared is 4. Which one of those two numbers is larger? 4. So now g of x is on top. I think I mentioned this last time, but let me say it again just in case. Don't assume that they're going to flip-flop each time. So pretty much all the ones we've looked at, they have, but that's not always guaranteed. More often than not, they do, but don't assume that it does, because there are some situations where the same function is actually on top in both intervals. If we were to do this graphically, we have x squared looking like this, and the square root of x looking like this. So looking at which function, so essentially they intersect at 1. So which one's on top of the other? Well, between 0 and 1, the square root is on top, but then x squared is on top for the rest, which is exactly what we just found algebraically. Once you find which function's on top of the other using one of those two ways, I mean, you can do both if you want to like double check yourself, but you only have to do one. We can now set up our integrals. So we have 1 from 0 to 1, and one from 1 to 4. I feel like I've been going very fast, so maybe I should breathe for a second. As always, tell me if I'm going too fast and you need me to slow down a little bit. So our integrals are always with the top function minus the bottom function. So in the first integral, the f of x was on top, so our top function was square root of x minus our bottom function of x squared. And then in the second integral, g of x now came to be the top function, so it'll be x squared minus square root of x. If you're doing these by hand, or shall I say by hand with a little help from a calculator for the arithmetic, the antiderivatives, forgot that word for a second, would be x to the 3/2, 2/3 in the front, minus 1/3 x cubed, plus c, I might run out of space if I put plus c, but I'll put it anyway, and then 1/3 x cubed minus 2/3 x to the 3/2 from 1 to 4. So I'm not going to write out the last step for that, but that's where you would have to plug in the top bound and then subtract what you get when you plug in the bottom bound. Well, actually, if you want me to show that, let me know. But if we plug both of those integrals into our calculator or finish calculating it out kind of by hand, we'll get 1/3 for the first one. And then I hate writing mixed numbers, but I'm going to go ahead and write this one as a mixed number. And then essentially 16.3. 16.3 repeating, really. So you'll end up with 16 2/3, otherwise known as 16.6 repeating, as your final answer. Any questions about that one? Or about this process in general? Because this is the last one from 5.3. If there are no questions, then we're going to jump over to 5.4. Okay. I'll leave that up for a few more seconds while I go grab 5.4. 5.4, I'm sorry for those who like to print them out. That got up just a little earlier today, so I'm sorry about that. Kind of late upload there. All right, so again, 5.4. So at this point, we've covered everything that will be on your exam. What we're about to talk about right now will not be on your exam. Will, of course, be fair game for the final, but will not be on your exam on Wednesday. So I need to share the correct set of notes. That's the wrong one. Where's 5? Oh, of course it's not actually showing up. Why would it? Fine, we'll do that. So 5.4, well, and these notes cover 5.5, but we'll only get through a little bit of 5.4 today. So 5.4 is essentially about interpreting integrals. So remember way back when we talked about the units and essentially the meanings of statements involving derivatives. That was when we had kind of those two different ways. We could phrase it as like a rate, or we could phrase it as a slope kind of idea. So now we need to talk about essentially how to interpret integrals. So remember that the integral is technically the limit of a Riemann sum. So remember, this is technically the formal definition of an integral, and it was that scary limit definition. But remember that the left side of this is essentially just a Riemann sum. So this scary, freaky looking thing here is just a Riemann sum. And remember that Riemann sums are essentially just sum of areas. So essentially, in that notation, since that change of t thought of as a small difference in t, because that's essentially what it means, then the terms being added are essentially a product of the form of something f of t times a small difference in t. So what I mean is essentially we're taking something that's a y value and multiplying it by essentially an x value. It's a change in x value, but so essentially the units of an integral are going to be the units of f of x or f of t, whatever variable you're working with, multiplied by the units of x. So it's the units of f of x times the units of x. Because if you think about it, if you think about what the Riemann sums were doing, we were taking widths multiplied by lengths. Well, the widths were x values and the lengths were y values. So that kind of makes sense that that's exactly what the units are here. One other note I want to make really quick is the units of the bounds. So if you have an integral with bounds, remember some of them don't have bounds, but if it has bounds, the units of the a and b are equivalent to the units of f of x. Oh, sorry. That's not right. Of just regular old x. So whatever the units of x are going to be the same as the units of a and b. So say, for example, we had some velocity function, so velocity equals f of t, and say that velocity function was given in meters per second, and time was therefore in seconds. So then if we were actually trying to figure out what the units of that integral would have, well, we're going to have the units of f of t, which is going to be meters per second, times the units of t, which is seconds. So essentially the seconds are going to cancel each other out and you would just get meters here. So if you want to take the units of the integral, units of the y value times the units of the x value. Since the units of the y value are usually a rate, they don't have to be a rate, but since they're usually a rate, the final answer usually ends up being just like a singular unit, if that makes any sense. So let's do a couple of examples of that. Wait a couple seconds in case people are still writing something down. So let's say we take this first example. Let me try to leave some of that in there. There we go. So this first example, let C of t represent the cost per day to heat your home in dollars per day. So let's keep track of some of the units we're working with. So we're working with dollars per day, where t is time measured in days. And t equals 0 corresponds to January 1st, 2018. Essentially, we're counting in days, and the 0th day is the first day of the year. And we want to interpret the integral from 0 to 90 of C of t dt. So before we actually try to figure out what this would mean in words, in context, maybe I should say, let's just figure out what the units would be. So the units of this, we need the units, essentially the y units and the x units. So the y values here are the C of t's. So the units of C of t are dollars per day. So dollars per day. That's going to get multiplied by the units of t. Was I saying x values? If I was, I'm sorry. So they were t here. So the units of t, which is just days. So let me just write day. So essentially the day units are going to cancel each other out. So this integral is just going to represent an amount of dollars. So now if we want to try to figure out kind of a sentence, if you will, to kind of explain what this means, let's try to figure out what that would be. Also, actually, side note, one last thing before we do that. The 0 and the 90, the units of those. So again, the units of the bounds are equivalent to the units of the x value, so in this case, the t value. So those are going to be in days as well. So essentially from day 0 to day 90 something. Okay, so if we think about what this means, this is an integral from 0 to 90. So we're starting at day 0 and ending at day 90. So C of t is the cost per day to heat my house. So if I'm taking the integral of the cost per day, That's essentially going to tell me the total cost over that amount of days. So I can interpret this and interpret. Is that how you spell interpret? Yeah, it is. Looks weird. Remember, in terms of interpretation with me, as long as it gets the point across, remember, I don't really care about your English, but essentially this is going to tell us the cost to heat your home for the first 90 days. So since this ends up being dollars, that should tell us that the final thing should be some kind of cost amount. And if it was telling us the cost per day to heat my house, this would tell me the cost, the total cost to heat my house. Well, to heat my house for how long? Well, that's where the bounds come into play. So it starts at day 0, goes to day 90. So that's where essentially the first 90 days is coming from. So that one. Questions, concerns on that one? Okay. Y'all are much quieter than my last class. All right. Keep that one up a little bit. Let's do a couple more of those. What is it? 138. All right. So say we want to interpret the integral from 1 to 3 of v of t dt, where v of t is in meters per second, so it's some velocity function, and t is in seconds. So let's do the units again first, and then we'll talk about the interpretation. So the units here, so units of v of t times the units of t. So we've got meters per second for v of t. Then we're going to multiply that by the units of t, so just s. So this is essentially going to end up just being in meters. So, and if you think about the original thing we started talking about integrals for, is we were talking about the area underneath of a velocity function for total distance. So this makes complete sense, as this essentially is going to come out to a distance. It's going to tell us a distance. So also, when you're thinking about an integral, it's essentially always over an interval. So it's always essentially telling you a change in some kind of value. So what this is actually going to mean here, interpretation, is essentially it's telling us the distance in meters. So distance, I'll put in meters in parentheses. So the distance traveled between t equals 1 and t equals 3. You could also say something like distance traveled in the 2 seconds between t equals 1 and t equals 3. The only thing you want to be careful with, so in the last one we did, I just said the first 90 days, but that was okay because I'm starting at 0. Here I couldn't say something like distance traveled in 3 seconds because it's not 3 seconds, it's 2 seconds. And I can't just say distance traveled in 2 seconds because 2 seconds when? Is it the very first 2 seconds? Is it the very last 2 seconds? Is it a middle 2 seconds? So in the last example, since I said first 90 days, that takes care of it. But here, since we're not starting at 0, we have to be really careful with how we state it. So you could say distance traveled in 2 seconds, but you also would need to tack on starting at t equals 1 or something like between t equals 1 and t equals 3. Just to kind of, you need to tell them where you're at. Questions on that one? Okay. We're going to keep going then. So the integral from 2005 to 2011 of f of t dt, where f of t is the rate of population growth in billions of people per year, and t is in years. So say I want to interpret that. So let's again focus on the units first. So the units of f of t times the units of t. So we have billions of people per year times an amount in years. Let me just write year. So the units of this integral are going to just be essentially billions of people. And again, an integral is essentially going over some period. In this case, it's a period of time in years. So this is essentially going to tell us the change in the amount of billions of people in 2011 versus the amount of billions of people in 2005. So it's kind of like the difference in the population, the change in the population between 2005 and 2011. So that's essentially what I'm going to write down. So the interpretation, it's essentially a change in that unit value. So it's a change in population. Let's say in billions of people. Between, that's too many E's. Between, oh my goodness, 2005 and 2011. So in this case, again, you could kind of say change in population over 6 years after 2005, but again, you can't just say 6 years because 6 years when. So you do need to be able to, you can either state the actual bounds, you know, both of the bounds together. You can say 2005 to 2011, or you can just use one of the bounds, but then you need some type of other verbiage to help them understand how far they're going. So you could say something like change in population in 6 years, starting at 2005. You didn't tell them it was up until 2011, but 6 years after 2005 will get you to 2011. So, questions, concerns about that one? Okay. We're gonna do one more. We might end a little early, but we're gonna do one more. So, no questions about that? Okay. Whoops, didn't mean to do that. So let's finish on this one then. So this one goes a little bit more in depth because it's actually going to ask us to calculate some values. So that's a little in the way. Oh, not really. So a man starts 50 miles away from his house and he takes a trip in his car. If he moves in a straight line and his house lies on that line somewhere, so say he just hops in his car and drives down a straight street for a while, his velocity is given in the curve. So the function that we're given here is the velocity function. And also I'm going to bold this line because I feel like that's the t-axis and I feel like it's just not clear enough. Anyway, so that's his velocity function. So essentially any positive velocity means that he's driving towards home, and any negative velocity means he's actually traveling away from his house. And remember, he starts 50 miles away from his house. Okay, so let me actually write that down here because I'm about to scroll down a little. Starts 50 miles from home. Let me scroll down a little bit. There we go. So when is the man closest to his home? Approximately how far away is he then? So he starts 50 miles away from home. And if we look at this velocity curve, he starts traveling towards home and he's traveling towards home, traveling towards home, traveling towards home. And then he hits 2 hours. And at the 2-hour mark, his velocity turns negative, which in this case, as we're told from the left side of the graph, means that he starts traveling away from home. So if he was traveling towards home up until the 2nd hour and then turns around, well, maybe he doesn't turn around, maybe he passed his house. But anyway, for some reason, he is now going away from his house. So the closest he's going to be at his house is essentially before he starts traveling away from his house again. So the closest he's going to be to his house is when t equals 2. Because he was traveling towards his house in that entire section. Now, A lot of times with this type of question, people will get very bogged down in the shape of this graph. Since this is the velocity, it tells us nothing about, well, it tells us if he's traveling towards or away, but kind of nothing else about how he's traveling towards or away. So don't get bogged down in the shape of the graph. Anything that's above the x-axis means he's traveling towards home. So he's traveling towards home all the way up until 2. So if we want to know approximately how far away he is from his house at that point, we essentially want to know how much he traveled in those 2 hours. If I want to know how much he traveled, that means that I essentially want to know this area underneath of this function at this point. Now, if we knew the function, we could set up an integral and, punch it into our calculator or do it by hand with an antiderivative, but we don't have the function here. So we kind of have to go back to that idea. You could do a Riemann sum here, but remember we did that one where we kind of just counted boxes and then we took into consideration how much area was in each box. That's probably going to be the better way to approximate this one. If you wanted to do 2 Riemann sums and average the 2, just taking 1 Riemann sum here would probably not get you a decent amount estimation. So let's do the counting boxes technique here. So we want this area between 0 and 2. So we've got, a little more than half a box in this first piece, and then maybe a little less than half a box in this second piece. So between the 2 of them, that's probably about 1 box, maybe a little bit more, but we're approximating here. So there's approximately 1 box under, was this given a name? No, the function wasn't given a name. Under the function between 0 and 2. But then remember, that doesn't actually tell us that he only traveled 1 mile, because we need to take into consideration the amount of area in each box. So these boxes, based off of the, what are they called? The labels on the axes, these are 1 by 30 boxes. So the area of each box is 30. So since the area of each box is 30, that is essentially going to tell us that, let me give this a name, let me call it v of t for the sake of what I'm about to write down now. So essentially, if we wanted to consider the integral of v of t, this would be approximately 1 times 30, so the amount of boxes times the area of each box. So we're going to say approximately 30 would be the area underneath of that function between 0 and 2. Now, we didn't answer the question fully yet. So essentially, between that time, he's traveled 30 miles towards his house. But we're actually asked how far away from his house he is. So if he started 50 miles from his house, drove 30 miles towards his house, he ends up 20 miles from his house. So the answer to the question this is actually asking is 20 miles, because it asks how far away from his house he is. So if he started 50 miles away and drove 30 miles toward, he ends up 20 miles away from his house. Okay. Questions about that before we do the second piece of this and then we're done? Okay. So now we're asked, when is he farthest from his house and how far away is he then? So there's kind of 2 choices here. Maybe he started out the farthest away from his house. Maybe 50 miles was the farthest he ever got. Or potentially, since he turns back around at 2 and then starts traveling away from his house again between 2 and 5, he could potentially end up the farthest from his house at essentially the end of his trip, because he's traveling away from his house during those last 3 hours. So let's go ahead and see how far away he is at 5, and then see if that's the farthest, or maybe he started the farthest away. So we're going to need to figure out how much he traveled between time 2 and time 5, 2 hours and 5 hours. So we need to find the area kind of below the x-axis for this function. So let's do the count boxes way again. So essentially we have 1 full box that's in here. And then essentially, if we start combining together some of the last pieces, we kind of have a second box between those two. But then between these over here, since this one at the very right is almost a full box in and of itself, and we do have this little piece of area down here. Whoa, sorry. I can't zoom when I want it to zoom, but it'll zoom randomly on its own. So let me do this again. Whoops. So we've got one full box. Kind of between these two, we get a second box. If we think about this very rightmost piece and this little tiny itty bitty piece kind of on the left there, if we combine those together, that'll probably be another third box. And then this last piece on the left is about half a box, a little bit more than half a box, but let's say that there's approximately 3.5 boxes between t equals 0, oh sorry, 2 and t equals 5. Now remember, each one of those boxes has an area of 30, so we can estimate the integral from 2 to 5, which will give us the total distance that he traveled in that time, as the 3.5 boxes times 30, which is the area of each box, which is about 105 miles. Now be really careful here. That doesn't mean that he's 105 miles away from his house. That means that he traveled another 105 miles. So how far away from how far away from his house is he at 5 hours? Well, if you think about it, he started at 50 miles. He drove 30 miles towards his house, and he got to 20 miles away from his house. So we already know that he kind of ended at 20 miles away from his house before we started this calculation, since we started at 2. So he's going to start 20 miles away from his house now, and travel an extra 105 miles away from his house, ending 125 miles away from his house. 125 miles away from his house is much farther away than 50 miles from his house, so we know that that was the right option, this last piece. So for this one, since we were given a velocity function, and we know that the area underneath a velocity gives us distance, we could take the area and use it as a distance, take into consideration where he started to kind of find where he was at any point. But specifically, we're asked for closest and farthest away. Questions, concerns about that one? That one usually throws people off a little bit. Okay. I'm amazed that we got that far, but that's actually all of 5-4. So anyway, but again, so on Monday, so we're going to stop there. I know we're 5 minutes, but we're going to stop there. On Monday, I think I said this at the very beginning, but we're going to start. I'm going to ask if anyone has any questions. If anyone has any questions about, it can be anything. If it's, well, not anything. If there's a specific question on the review packet that you want to go over, we can go over that. If there's a homework question you want to go over, we can go over that. If there's a topic you want me to just give you more questions for, we can do that. All that jazz. And then if there aren't any questions or it doesn't take up the entire time, we'll continue with these notes, but that's what we'll be doing. Lorenzo. Oh wait, I know what it is. Why do I? So first of all, they're also listed in the review packet, but they are. Let me just write them here really quick. It's 5-1 to 5-3, and then 6-2 to 6-3. So this was the antiderivative stuff. Can I write? Oh my goodness, antiderivative stuff. This was Riemann sum, and essentially this stuff we're talking about right now, the area stuff. If I'm quite honest, there's not a huge amount of content on this exam. We usually we get through a bit more before this last exam, but that's what it'll cover. The topics are also on that review packet. So it goes over kind of what each one of these sections covers and all that jazz. But anyway, I'm going to stop the recording here. If you have any questions, feel free to